Hello all. So in this lecture we will be seeing channel capacity. So this is under information theory. So the question here is how we measure the amount of information that we transfer through the channel. So as we all know, we transfer information through the channel from transmitter to receiver. So this is our TX and it's our RX. Then we transfer some information, right? So how we can measure such abstract quantities called information? So is there any way to write in terms of mathematical terms or something? So let's try to see it. So basically, as we all know, the information that we transmit is in the form is generated by some source, right? And we know that since this information sources generate random information, right? So this is a random information. So the output of the source is characterized in terms of statistical terms, right? So there are sources like DMS, right? In case of analog sources, there is totally different theory, okay? But since we are in digital domain, so we'll be discussing specifically about discrete memory-less source. So this is a discrete memory-less source, and we know that this output of this discrete memory-less source is statistically independent, right? That is, we can say that the output of the current output of this DMS will be independent of its previous output. So current output has no relation with previous output. And in examples of English text, like we know that English text is dependent on each other, right? First output is will be dependent on each other. So in that case, we'll be constructing the mathematical model of this information source based on some assumption like stationarity and all. So I'm not going deep into all this stuff, right? What is stationarity and all, but because that is not needed particularly in this chapter, general capacity. So let's focus on how to characterize the information. Back to our topic, that how to characterize our information, how to measure the information. So let's say we have two random variables x and y are two random variables. So I'm writing just RV. So let's say the possible outcomes of x is xi, where I range from 1 to n. Since this is discrete memoryless sources random variable, so that's why we are having discrete things corresponding to the random variables. So and similarly for y, let's say small yi and yj to be just to differentiate, and it will range from, let's say, 1 to m. Okay, so both have different indexes. Now we know that suppose we observe some outcome of y, let's say y equals to yj, and now we want is and now we want to determine, obviously quantitatively, because we are considering everything of about information, so quantitatively we have to determine the amount of information, so the amount of information that the occurrence of this event y equals to yi, occurrence of event y equals to yj, sorry, provides about event x equals to xi. So let's say there is some other event x equals to xi. So what is, we can say, what is the amount of information this yi will give if we observe yi about xi, right? Of course, if x and y, if they are statistically independent, if okay they are statistically independent, then obviously the occurrence of y equals to yj won't provide any information about x equals to xi, of course. But if they are dependent, mind my words, if statistically independent, then y will not provide any information about x and vice versa. But on the other hand, but when x and y are dependent, or you can say fully dependent on each other, like rolling a dice. So all outcomes are fully dependent, right? So because if one will come, then two won't be coming at a time. One will only one individual, or you can say distinct number, can come, right? So when both x and y are fully dependent, then such that so when x and y are fully dependent, such that the occurrence of y, the occurrence of event y equals to yj determines the occurrence of x equals to xi, then the information content is simply provided by event x equals to xi, right? Because since both are dependent, we can say that. So we want some mathematical formula for the same, that how much dependency is there between x and y, obviously the information, right? So the information content provided by the event y equals to yj about the event x equals to xi can be defined as, so I am repeating, that the information content provided by the occurrence of event y equals to yi about the event x equals to xi is defined as, sorry, y equals to yj. Okay, so we can say that it is denoted by this, that the information content I, which is provided by the occurrence of event y equals to yj, okay, let it be j, about the event x equals to xi is defined as something like this, that log to the base 2 probability of the conditional probability that given yi, what is the probability that xi will occur, divided by probability of xi, right? So and this xi, that this I is called, and this I is called mutual information, or it's called mutual information between xi and yj, correct? And obviously the units will be bits, we are in digital domain, right? So let's consider a lame example, the naive example that I am considering, just to have the understanding. So naive example will be, let's say the probability of getting snow in some country which is located near poles, okay, that is USA, in month of Jan or Feb, in winter especially, will be zero point 0.8. But as we all know that the probability of snow in some countries like Australia in winter, not, I mean not in winter but in Jan, in the same month, because in Australia it will be summer in Jan, right? So let's say it will be very less, let's say 0.2, right? So and let's say the probability of just having snow, it is average probability, okay, this the last one that I am writing is average probability of having snow anywhere in the world, it's not fixed that where, okay, it's let's say zero point 0.3. So I'm just writing here only that the information of snow in Finland will be log to the base 2 0 0.8 divided by 0 0.3, and which will be some positive value. If you can calculate, you will get some positive value about 1.5 or something. So it is positive, so it implies that positive correlation between the two events x and y, that is xi and yj, and it means that highly likely that it will snow, highly likely to snow. But the similar thing if you will calculate for Australia down here, okay, so it will be divided by zero point 0.2, right? It will be 0.2 divided by 0.3, and here we will get some obviously negative value, and this implies negative correlation, and this implies no snow, right? So this is how this mutual information between two events xi and yj is characterized, right? So the some are the some special cases let's consider. So first one is when random variable x and y are statistically independent. As I already said this, but I am just considering in just for sake of completeness of properties. So when they are statistically independent, so what will happen? We know that when two events are statistically independent, we can say that the probability of xi given yi has already happened will be same as probability of xi only, right? Because they are independent. So if we will put that thing here, okay, so inside the log both will cancel, and we know log 1 is 0, right? So we will get 0. So it means that when they are statistically independent, as I already said, there will be no information, right? No mutual information will be there among two random variables x and y. Then the second property will be, let's say that p of xi comma yj will be equals to 1, and when this will happen, when, let me write in terms of words, that this will happen when the occurrence of the event y equals to yj uniquely determines the occurrence of event x equals to xi, right? It means that given yj has already happened, right? The probability of having xi, that is the probability of event xi, will be 1, right? And if this will be 1, then our mutual information formula, this is mutual information, okay, will be simply equals to 1 upon pxi. Now we know that this formula is no longer dependent on, you can notice that this is no longer dependent on yj, right? So we can just simply write it as information of xi and will be equal to log to the base 2 1 upon p of xi, which is equal to minus log to the base 2 p of xi. So, and this is called the self information, that is the probability, the information of xi with itself. So what is the information that we are getting, okay, when event xi is happening? And that's why it is called self information. And this is very important. Let me give one intuition of this mathematical term, that what does this mean? It means that the information attached, okay, that or the information that we get from occurrence of any event is written as something like this: minus log to the base 2 and the probability of occurrence of that event. So what does it mean? It means that when the occurrence of event, that is the probability, is higher, right, then the information will be more and more negative. As probability of occurrence of event xi is higher and higher, we are getting the information, okay, attached to that event lower and lower. It means that the probability of rare events have more information, because rare event will have less probability, and less probability means less negative, so more will be ix. And it is same in real world, right? That what news channel, we watch news, right? What news channel will show? They will show the rare events only, because with rare events the information is higher. And this is what Murray's code is saying, right? You can, I hope you can compare it with Murray's codes, okay, the Murray's law. I'm not going into that, but it's your homework, that just make this intuition that how Murray's code was working, okay. So let's move forward, not going deep into this now. mm, let's say we have, let's consider one concrete example for a deep understanding. So a discrete information source, let's say there is some source again emitting the discrete information, and it emits either binary digits 0 or 1 with equal probabilities every tau seconds. Let's say tau s seconds. So the information content, that is the cell information, okay. So the information content of each output from the source is given by self information, simply I of xi, and it is equal to, we know, minus log to the base 2 p of xi, right? And we know that what is this p of xi? P of xi will be 1 by 2, right? Because we are assuming that with equal probability our source is transmitting either 0 or 1, right? So the probability will be of each output will be half half, 50-50%. So this will be 1 by 2. So it will, what we will get, minus log to the base 2 of 1 by 2, which is nothing but 1. And in terms of bits, as I already said, so we are getting just 1 bit, right? Now suppose that, so you can characterize that what we are getting 1 bit at a time every tau second. So we are getting the information as 1 bit. So we can say that this is our valid intuition that we developed using the probability of base 2, right? Now suppose the successive outputs from the source, from the same source, okay, are statistically independent. That is, we can say that, as you already see in this case, it is a memoryless source, discrete memoryless source. So now in this case, what will happen? Now in this case, since it is transmitting a stream of bits, consider a block of k binary digits from the source, and obviously it will occur in time k into tau seconds, because now there is k binary bit, right? And we know that there will be m equals to 2 power k possible k bits. For k bits it will be 2 power k possible symbols, right? And each with equiprobable, and what will be the probability of each? Will be 1 by m, because in total we are having m symbols, so probability, and since they are equiprobable, we have 1 by m. So now what is the information attached in this case? The self information, and we know that it is given by log to the base 2 1 upon p of xi, or minus log to the base 2 p of xi. And we know what is p of xi will be equal to 1 upon 1 by m, which is nothing but log to the base 2 of m, and we can substitute m as 2 raised to k. So at the end we are getting k bits. So we can say that these examples, these are naive examples that I considered because just to validate our intuition that we developed using mathematics, that the abstract quantity like information, how much the information is there in the occurrence of one event in terms of bits, how much is there that we just get from this, right? Now let's finish off this lecture by discussing some properties of our mutual information, right? So properties. So mutual information is the one from where we started, right? So properties of I of xi comma yj. So the very first property is that I of xi yj will be equal to same as yj xi. Doesn't matter, right? And the proof is very simple. I'm just quickly going through it. That we know that this mutual information is given by something like this. I'm not writing the exact thing, the logarithm, but we know that it's given by, the argument is this inside the log. Let me show you that where it went. Yeah, so here log to the base 2 of this thing. So we know that using Bayes rule of probability, we can substitute this as, let me go again there. So using Bayes rule, we can substitute this as let me firstly, for that we will need something, that I am just multiplying, pardon, uh, probability of xi yj into p of yj. I am just multiplying both numerator and denominator by p of yj. That's it. Okay. Now this can be written as, the above thing, numerator can be written as p of xi and yj. That is probability of combined occurrence of xi and yj, and the denominator as it is. And now this term over here, that is this, can be again written as p of yj comma xi, that is probability of occurrence of yj given xi has already occurred and yj is as it is again. And we know that this is nothing but the inverse of this. We can consider this, the xi and yj are flipped over here, right? So whether we flip here, it doesn't matter, right? So in words, I'm just telling, just take a note of it, that the information provided by the occurrence of event y equals to yj about the event x equals to xi is identical to the information provided by the occurrence of the event x equals to xi about event y equals to yj. It's very simple, right? So there is something called conditional cell information as well. These are some quick small definitions, new terms, so I'm just quickly going through it. So what is conditional cell information? So we know our cell information definition, right? So in that, just we are having now the condition that xi and yj, that's it. So it will be just we are having the conditional probability instead of simple probability of the event xi yj, and this is nothing but our conditional self information, that's it, right? Now there is something, there are some properties of mutual information as well. So let's continue to discuss that. We discussed here, pardon, we discussed here about the first property, that this is equals to this, right? Now I don't think there are some other properties of the mutual information. Yeah, I think, yeah, this only suffice. Now there is something called average mutual information, right? Now how to derive through that concept, how to go through the concept. So I will develop the intuition to go through the concept of average mutual information. We started with mutual information, right? And then we from that we derived one thing, that is called self information, which is independent of yj, just depend on xi. Now again let's go back to mutual information, and again from the mutual information we will go to average mutual information, right? So let's try to just develop the intuition and wrap up for this lecture. So again I am writing the mutual information definition from where we started with our intuition, that it is given by log to the base 2 p of xi given yj upon p of xi, right? Now using the logarithm properties, we can write this thing as p of xi yj minus log to the base 2 of p of xi, right? Now we can write this thing minus log to the base 2 p of xi. We already know which is nothing but the self information, and we just saw this is nothing but the conditional self information, right? So we can write like this. Okay, I'm just writing this thing along with minus is there, so first term will be positive and minus, here it will be minus. Okay, just note the sign, just see here what is the definition of conditional. So if we will take probability above, here we will get minus sign. Okay, so that's why here minus I of conditional probability. So just writing it I of xi comma yj. So we can see that our mutual information, that is from where we started, can be written in terms of self information and conditional self information. And there are three things that we can see from this. We can observe that clearly that when this term, that is conditional self information, is greater than this term, our mutual information will be negative. And we calculated our mutual information in terms of the snow in USA and in Australia, right? So if this is greater than this, then we know that we will get this thing as negative, that is there will be no snow, right? I'm just connecting the things that I already discussed, so please stay tuned and pay attention. Similarly, when first term is greater than second term, obviously then our mutual information will be positive and there is highly likely to snow. And when these two are equal, right, then there will be no information, no mutual information, right? So from this is the mutual information, right? So the summary is that we started from mutual information, we derived one term called self information, then conditional self information, then again we came to mutual information, and uh, we can say we just wrote the expression of mutual information in terms of self information. This is our self information and this is our conditional self information, right? Now we will extend this concept further for the average mutual information. So we will take mutual information but average. So we will see how we will get through the average. So that's it about this video. Thank you.